Hello guys, my name is Subham and I am yet back with another video on one of the most important concepts in strength of materials, that is resilience and toughness. We are going to see not only what is resilience and toughness, but also we are going to see the different types of resilience and toughness with the help of graphs. It will be very easy for you to visualize things with the help of graphs, and also understanding any concept with the help of graphs. You can remember it for a longer time. So without wasting any single time, just we will start with the concept of this resilience. But before this, I want you to understand this concept, that area under the load deflection graph gives us strain energy. Just tell me one thing, that what does the area under force displacement graph gives us? It gives us work done. So suppose that if we are stretching some body and we are doing some work on this body, so that work is being stored in this body in the form of strain energy. That is what is written there, strain energy. Area under load displacement graph gives us work done, which is stored in that body is in form of strain energy. Whereas if I talk about area under the stress strain graph, it gives us strain energy per unit volume or strain energy density, which is in units of joule per mm cube. So this gives us strain energy density. Just tell me one thing, that what is density? Density is a kind of intensive property. And what is intensive property? It is any property of a material which does not change with the quantity of object. Let's suppose if we take either aluminum, copper or steel, so their strain energy density will not change for a given load, and its unit is in terms of joule per mm cube. We take a 1 mm cube, and what is the energy stored by that 1 mm cube, just that value we have to find out, which does not depend upon the quantity of that material. Suppose we take 6 mm cube of aluminum, or we take 6000 mm cube of aluminum. So in both the cases, the strain energy density will not change. Just a second. So I hope that you must have understood these two things, that area under load displacement graph gives us strain energy, and area under stress strain graph gives us strain energy per unit volume. So starting with resilience, before this I want you to know one thing, that these three graphs, resilience, proof resilience and toughness, these are on load deflection graphs. So what does the area under these graphs gives us? It gives us strain energy, and these two graphs are on stress strain graph. So what does the area under these two graph gives us? It gives us strain energy density. So that is what is written there, strain energy per unit volume or strain energy density. And so these three graphs belong to one category, load deflection graphs, and these two graphs belong to one category, stress strain graphs. So starting with resilience, resilience is nothing but the amount of strain energy that is stored in a body within the elastic limit. Suppose if there is an object and I stretch it within the elastic limit, then the amount of energy which is stored in that body is termed as resilience. Proof resilience is nothing but a special case of resilience only, in which we stretch this body up to the elastic limit, not beyond elastic limit and not within the elastic limit. So proof resilience we can call to be a special case of resilience in which we stretch the body up to the elastic limit. Okay, and let me ask you a question, that what is the difference between elastic limit and proportionality limit? If I talk about proportionality limit, it is the limit up to which Hooke's law is valid. What is Hooke's law? Stress is directly proportional to strain. So if we replace this proportionality sign with constant, so it will give us a linear variation passing through origin. So Hooke's law is valid up to proportionality limit, but in case of proof resilience, it is valid up to elastic limit, and the Hooke's law is valid up to proportionality limit only. It is not valid up to elastic limit. Elastic limit is the limit up to which any object shows its elastic behavior. So both these points are conceptually different, but they are so close to each other that sometimes to make calculations simpler, we take both the points as equal. So this concept you should know that what is the difference between both these points, and that's why you can see here that I have written the stress value at proportionality limit over here, and whereas you can see the stress value at elastic limit I have written here. And we are going to see these two formulas. These are important for solving numericals for exams. So before understanding that let's say here that what is strain energy density. It is the area under the stress strain graph. So suppose that this is the area under stress strain graph, and here this graph is following linearity. Why? Because due to Hooke's law. Due to Hooke's law, this graph is showing linear variation passing through origin. So we can take out the area of this triangle, which I have done here, half into stress into strain. This is the area of this triangle, and this strain we can replace upon by sigma upon E. So it will come out to be sigma square upon 2E, that gives us strain energy density. And this E is Young's modulus of elasticity of the given material. So what is modulus of resilience? It is the strain energy per unit volume stored up to proportionality limit. So that is what I have written here. This is strain energy density. That term only I have written here, that the area under this graph gives us modulus of resilience, which is nothing but strain energy per unit volume up to proportionality limit, which will be in units of joule per mm cube. But on the other hand, this proof resilience should always be come in terms of joule. Why? Because the graph under it gives us strain energy. So strain energy per unit volume multiplied by volume will give us strain energy, which will be in units of joule. So all the concepts I have explained, and these graphs can vary with the type of by varying the type of load. Suppose here we are applying a gradual load, but it can be a sudden or impact load also. So these three graphs can change with the type of load, but these two graphs can never change at any case. So you must have seen the stress strain graph of mild steel. Does its graph change? No, it never changes, because it is the property of steel. So that's why these graphs never change, but these three graphs can change with the type of load or any other variation that we do. So this was all about resilience and toughness. And if I explain about hardness, then hardness is the ability of a material to resist any scratch on its surface. So hardness is a surface property, but on the other hand, these resilience and toughness are bulk properties. These are the property of the whole material, but hardness just has connections with the surface of that material. So this was all about the concepts of resilience, toughness and hardness. And if you have any doubt, just ask that doubt in the comment section. I will try to resolve all your doubts.